introduction. Good morning, everyone. My name is Qimin Zhang, and I'm from the University of Oklahoma. My advisor is Arne Schwettmann, and today I will present our experimental progress of forward mixing in a hot sodium vapor cell. And this is a picture of our experimental setup. So why are we interested in forward mixing? Because forward mixing is a nonlinear optical process which can be used to generate quantum entangled light. For example, if we have a pump and probe beam interact with a nonlinear optical medium, pairs of entangled probe and conjugate photons can be generated. And the entangled light has many applications in quantum information processing, optical parametric amplification, quantum enhanced image, and so on. We are particularly interested in using forward mixing to generate entangled sodium resonant light at 589 nanometers to improve the absorption image measurement of our sodium BEC. This cartoon shows how this might work. One of the entangled beams is absorbed by the BEC, and we can analyze the intensity difference afterwards to get the number of atoms inside the BEC. This is an image of our current measurement. The three clouds here are the three spin modes of a spin 1 BEC. So my goal is to improve this imaging result by using entangled light. We use a double lambda configuration on sodium D1 line. F1 and F2 here are the hard-find states of the ground state, and this is the first excited state. And the two pump photons can be absorbed and converted into a pair of probe and conjugate photons at the same time. This is our experimental setup. Our pump and probe beams are derived from the optical SSG yellow probe system at 589 nanometers. This is also used in our BEC experiment. Our pump and probe detuning can be adjustable through this 1.7 gigahertz AOM. And we use a Pyrex sodium vapor cell and a home-built oven to keep the cell windows cool to prevent the sodium condensation on the windows. So this kind of configuration and setup works very well for the experiments using other alkaline atoms. And this is an example of measurement of forward mixing on rubidium from Marino's group at the University of Oklahoma using similar configuration and setup. They have got a noise squeezing of about 9 dB below the show noise. But for sodium, we have some challenges. The first challenge is the vapor pressure. Here we are looking at the vapor pressure versus the temperature. At the same temperature, about 120 degrees C, the sodium vapor pressure is about 3 magnitudes lower than the rubidium. So it requires much higher temperature for sodium. And we use a temperature above 160 degrees. But the temperature is limited because the sodium reacts with glass cells at temperatures above 120 degrees. And we also use long vapor cell, which is 3 inches, to interact with more atoms. And the other challenge we have is the Doppler-broadening. Here is the D1 line of sodium and the rubidium. We can see that for sodium, the half-time splitting is only 1.7 gigahertz compared to 3 gigahertz for rubidium. So in absorption spectrum, the two dips for sodium overlap, but for rubidium, there is a larger spacing. So this causes more absorption loss on forward mixing signals in sodium compared to rubidium. Here I'm showing our forward mixing results. This is the intensity versus the laser frequency. And the blue line is the absorption spectrum without the pump beam. And the red line is the probe signal with pump beam. We can see there is a big amplification. And at the same time, the conjugate signal is generated. This plot is from the oscilloscope. The probe and conjugate peaks appear at the same time, but their frequencies are different. The probe frequency is at about here, and the conjugate signal frequency is at about here, which is inside the absorption dip. So this causes more absorption loss during the forward mixing process. So for rubidium, you can see the conjugate signal, the frequency is far from resonance. So it has much less absorption loss. By optimizing the parameters like temperature, detuning, the angle, and so on, we observed forward mixing signals with the gain up to 6. Here we are looking at our forward mixing noise measurement. So this is a normalized noise versus the frequency. The blue and the red line, the green lines are the single beam noises of the probe and conjugate beam. The black line here is differential intensity noise between probe and conjugate measured by a balance detector, and with an attenuator here on the probe to compensate the conjugate loss. And the red line here is the shot noise. We can see that our differential noise is very close to shot noise. It's about 1 dB above shot noise. So here we didn't observe the squeezing because we have a diode laser that introduces intensity and frequency noise. The SHG system converts frequency noise to additional intensity noise. And we also have a very large conjugate loss, which is about 80%, and a large probe attenuation to compensate conjugate loss. And we also did a calculation for our squeezing. So the RAB here is the ratio of differential intensity noise and shot noise. The eta here is the light transmission ratio, and G is the gain of the forward mixing process. We used our current parameters at the temperature of 160 degrees. We found that the maximum gain maximum squeezing we can get is less than 1 dB. So here the blue line is the expected noise by shifting the shot noise down by 1 dB, and the black line here is our measured noise. So this small squeezing is very difficult to observe. So how can we improve squeezing? Since squeezing depends on gain and also the loss, we can increase the gain or reduce the loss. So this is the calculation of squeezing versus gain for different losses from large loss to small loss. We can see that in the presence of large loss, increasing the gain only does not effectively increase squeezing. But by reducing the loss, the squeezing can be enhanced a lot. So we use an extra laser beam, which is counter-propagating with the conjugate to reduce the conjugate loss. And by applying this saturated absorption light, our probe and conjugate signals can be enhanced by about 50%. So this makes a noise reduction of about 2 dB. Here we are still above shot noise because when we were taking this measurement, our diode laser noise was higher on that day. And we believe that if we can reduce the laser noise, we will be able to observe squeezing. Here are my conclusions. We observed probe and conjugate light through the forward mixing in a hot sodium vapor cell. We characterized and optimized the forward mixing process to obtain the largest gain. We reduced the differential intensity noise between the twin beams to close to our shot noise level. We are applying an extra saturated absorption light into the vapor cell to reduce the probe and conjugate beam losses, which will further reduce the differential intensity noise. We are looking into high-speed noise eaters to reduce intensity noise on our lasers. Thank you for your attention.
Questions?
For this temperature of the cell and the power,
yes.
How much absorption or transmission for each your probe and power?
And in 160 degree, our conjugate transmission is about 20%, or in other words, the loss is about 80%.
Okay, so but then there's significant power change across this 3-inch cell. So this forward mixing process may have different strengths for different positions.
Yes.
So does it affect these measurements? Basically, this is inhomogeneous volume.
Yes, by moving the cell position, that losses changes a little bit. That's what we found in the experiment.
So how sensitively does the noise reduction depend on the mismatch between the angle mismatch between the conjugate beam and the extra beam? And also, what's the major advantage that sodium is offering that rubidium? I mean, what do you hope to gain?
Okay. So the first question is the angle, the noise sensitivity on the angle. It's we found it was sensitive, and then we optimized the angle. We found that for our setup, the angle we used about 0.1 degree. That was about the best result we can get. And the advantage of using sodium for mixing is we want to use the sodium to generate a sodium resin light that can be used in our sodium BC experiment.
You use an attenuator here to try and balance the beam on this. That adds more losses.
Right.
Could you just separate the detectors and put more gain on the conjugate detector? That might help reduce the effective loss of correlations. I mean, it might be better than attenuating given how high your losses already are.
Okay, good. Thank you.
Is there anything else?
Your saturating beam, which has to be at a very similar frequency to the beam that you want to saturate and therefore increase the transmission.
Yes.
How hard is it? Do you get excess noise from reflections or anything from the cell when you put this saturated beam?
The saturated light we are using is from a dye laser, and that laser is actually pretty noise on intensities and frequency. That does add some extra noise. The noise from reflection or other things, I think these noise are smaller than it's not the main major noise we can see now.
Okay. Yeah, I would think that the saturating beam might also affect your optical pumping in the vapor cell a little bit as well, so that could be an issue. All right, so I think we can stay on time and